Hi everyone, welcome back. Thanks for coming on time. So what we're doing is we're continuing our exponents, except we were working at radicals before, and radicals are a type of exponents. So let me go ahead and flesh that out for you guys. Someone just came in. Let me flesh that out for you guys. Yeah, let someone in real quick. Okay, so the first thing is, let's look at a radical such as a square root of, come on, pen. The square root of 4. We know that the square root of 4 is 2. Okay, something that we worked on before. Now, I want you guys to rewrite this as an exponent. And if you might remember this from Algebra 1, maybe you didn't cover it. But we can rewrite this exponent as an exponent of 1 over 2. Well, why is that? Let's look at it a different way. If I write 4 to the 1 power, isn't that just 4? We have 1 4. And when I'm looking for fractions like this here like sets. I have 1 out of 4. So I'm looking for a set of 2. Now, let's rewrite this a little differently. If I look at 4 as a 2 squared, isn't 4 just 2 squared? And we have a rule when it comes to power of powers. I'm not sure you guys remember this. The rule goes, let's say 3 squared to the 4th power is 3 to the 8th power. Because 3 squared times 3 squared times 3 squared times 3 squared means you have 1, 2, 3, 4, 5, 6, 7, 8. You could write them out, or you could just multiply them. You can say it's just 3 to the 2 times 4, which is 8. We can do the same thing even though it's a fraction. 4 is really 2 squared. And what happens to those exponents if we multiply them? 2 to the 2 times 1/2 is 2 over 2. Take a look at what happens to the fractions. They cancel out, and we're left with 2 to the 1, which is just 2. A long way of just doing that. Okay. You might say, Mr. Ko, I know that square root of 4 is 2. Yes, because that's our really basic version of it. But let's look at another one, and let's look at 64. The square root of 64. Okay. And we know this is 8. Right? So I'm going to go ahead and spin this around. And we'll say this. How many 2's are in 64? Just to rewrite this, it's 2 times 2 times 2. That's 8 times 2 times 2 times 2. So we have actually the square root of 2 to the 6th power. Okay. If I rewrite this the way we did before, 2 to the 6 to the 1/2 power. Or you could just write 2 to the 6 over 2, because we can express our radicals as a fractional exponent. We can express our radicals as a fractional exponent. This becomes, we just wrote it, 2 to the 6 over 2, which becomes 2 to the 3 power, which is back to 2 times 2 times 2 is 8. Okay, so we're saying that us doing it this way, writing it as a fractional exponent, is not giving us a different answer. It's giving us the same answer. It's a different approach to look at things. Now, why is this kind of helpful? Is because for numbers, great. But what if I give you the same idea? If I write 64, but this time let's write the cube root of 64. Using our 2's, how many 2's give us 64? We said 2 to the 6. Whoop, not 26. Let's rewrite this as a fractional exponent. 2 to the 6 over 3. Is everyone okay for me skipping that step? You could have written as 2 to the 6 to the 1/3 power, which then multiplies 6 times 1/3 is 6 over 3. We can simplify 6 divided by 3, can't we? That's just 2, which is 4. It turns out 64 is 4 times 4 times 4, and the cube root of 4 times 4 times 4 is just 4. Okay. So our goal today is just to be able to rewrite our rationals as exponents and understand that they're really the same thing. We're just looking at it in a different way of writing it. Okay. So what if I want to go backwards? What if I write 5 cubed over 4? How would this radical look? How would this look in radical form? Well, this would look like 5 inside cubed with the fourth radical there. Does this simplify out? Do we have enough 3's to get out? Well, already here you see that with 3 out of 4, we don't have enough 3's to go out. What if I wrote this as 5 to the 4 over 3? Let's spin this around. Okay, we could have said, well, we have 5 to the 4th power. We have 4 5's, and we're looking for sets of 3. Well, two ways of looking at this. We can say, okay, hey, can we simplify that fraction to be 5 to the 1 and 1/3? So the way you want to see this is we actually have 1 out. So this is really 5 times 5 to the 1/3. That's a 3. Which can be rewritten as 5 times the 3rd root of 1 5 inside. And that's exactly what we would have done here. We would have said this is 5, 1, 2, 3, 4. We're going to take out 3 at a time. 5 left over, 1 5 inside. Looking for sets of 3. Looking for sets of 3. Okay. If I give you guys, let's do 9x cubed all to the 1/2 power. This is the same as the square root of 9x cubed. Why? Because this 2 refers to that square root here. Now, looking at this both ways, if you guys remember our powers, when it comes to multiplying, we can separate those 9 1/2 and x cubed over 2. We can write it this way. If you can distribute that exponent, because there's no plus sign inside, no plus or minus. And what is the square root? See, that's actually a square root of 9. This could be rewritten as 3 squared to the 1/2 power. Well, that becomes just 3x left over times, oh, let me rewrite this as x to the 1 and 1/2. We can rewrite that as I have 1 full x out. See, this guy is 1 full x out. No more fractions. It's not bounded by anything. And then we have 1 left over in the square root. What if we treat it like we normally do? This is 3 times 3. I have 1, 2, 3. And we're looking for sets of 2. I have 1, 2. These guys get to come out. We have 3 and x get to come out, but we are stuck with 1x on the inside. I'll say this way works more visually, of course, right? Because you're just looking for sets, but it is slower. It takes up a lot more time because you have to write down all the possibilities. I mean, you have to spread them all out. Okay. Let's jump to a larger one. What if I write 243 and I'm looking for 1 over 5 exponent, 1 over 5 exponent. This could be rewritten as the 5th root of 243. Now, I don't know what 243 is made out of. I'm going to write on the side 243, and we're going to start dividing it. What's the easiest number to divide by 243? It's not 2. Maybe some of you guys are thinking 3, perhaps? Is this number divisible by 3? Can you divide this number by 3? And if you remember the rule, I'm not sure if you guys know this already, but the rule is if you add up all the numbers, and this becomes 9, can you divide this new number by 3? And if you can, the original number can be divided by 3. 3 goes into 2, doesn't. 3 goes into 24 8 times, and 3 goes into 3 1 time, 81. Does 3 go into 81? Well, we know it does, but if you want to use our trick, 8 plus 1 is 9. Yes, and 9 can be divided by 3. We can divide this by 3. That becomes 3 goes into 8, 2 times, remainder 2. 3 goes into 21 7 times. So I'm just dividing here without any special rules. 3 goes into 27 9 times, 3 and 3. We take a look, we have 1, 2, 3, 4, 5. We have 3 to the 5th power, 1 over 5, which is 3 to the 1 power, right? Oh, let's write it, 5 over 5, which is 3 to the 1, which is just 3. Turns out if I have 1, 2, 3, 4, 5, we have enough 3's to come out. So what's the difference between us writing it as an exponent or us leaving it in radical form? Nothing. It's just a different way of writing it. What if I give you something a little bit weird? What if I write 32 9 over 5? 32 9 over 5. There's a couple of different ways of doing this. We can write 32 9 times. We can multiply 32 to the 9th exponent. But I'm going to show you guys a couple different ways of doing this. There's a couple, okay? Let's do one way of, let's convert the 32 to a bunch of 2's. 32 is really 2 to 16, 2 to 8, 2 becomes 4, and 2 and 2. And you see this is 1, 2, 3, 4, 5. This is 2 to the 5th to the exponent of 9 over 5. Is everyone okay with how I got 32 is 2 to the 5th? 1, 2, 3, 4, 5. 32 is really 5 2's. Now what happens to this 5 here? What happens to this 5 here and this 5 here? Well, if you don't see it, we can multiply it. This is 2 to the 45 over 5. Hey, don't they divide out? Which is 2 to the 9. Or hopefully if you notice that these guys would have just divided out. If I wrote it as 2 to the 9 times 5 over 5, the 5's would have divided out. Okay, so, and then we end up with 2 to the 9th. What's 2 to the 9th? I don't know, a big number, right? So we know 2 to the 5th is 32. So if we multiply another 1, 2, 3, 4 2's to it, this will become 64. This will become 128. This will become 256. And this will become 512. So this answer would have been 512. Well, let's look at another way of doing this. Not necessarily the brightest way. But if I went ahead and I said, well, hey, doesn't 9 divided by 5 simplify out? So we have 32 to the 1 and 4/5 power, right? Because 9 divided by 5 is 1, the remainder 4. So we can say this is really 32 times 32 to the, that's right, read as the 5th root of 32 to the 4th power. And this isn't the smartest way, but this is going to give us the same answer, no matter, regardless of what I'm saying. It's going to be 32 times, okay, we're going to have to figure out breaking up that 32 to become, let's just say 2 to the 5th power. I think that's the easiest way. This is 2 to the 5th power times 4, all in the radical 5. This is a messy way of doing it. 5 times 4 is 20, 2 to the 20, the 5th power. We still have 32 waiting for us in the front. Remember, 32 was a whole one that came out of the radical already. Now, how many 2's do we have? We have 20 of them, and we're looking for sets of 5. So this reduces down to 32 times 2 to the 4th power, because 20 divided by 5 is 4. Or if I want to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? Each of these become a single 2. Just to wrap your brains around it if you guys haven't figured out what radicals are. So that's why we have 2 to the 4th. 2 to the 4th is 2 2 times 2 is 4. 4 times 4 is 16. This is 16. 32 times 16 is some atrocious number. 32 times 16 is going to be 512, right? But let's go down and show you guys. This is 2, 1, 18, 19, 0, 3, 2. This is 4, 5, 1, 2. Yep, same answer. So the point is, there's a lot of different ways of doing these problems, but you want to find the most efficient way. And I feel like the most efficient way is change the exponents, then we can simplify the exponent as much as we can, and then, hey, we might be out of the fraction. And if we're out of the fraction, we're back to easy street. It's something that we don't want to be too scared about, we don't want to freak out about. Okay, so let's give you guys another one. If I say 243 to the 6 over 5 power, we can rewrite this if you want as the 5th root of 243 to the 6th power. And we can do what we did before. Hey, we have 6 of these, we can remove 5 of them. That means we're 243 on the outside with the remainder of 243 on the inside. Because we got rid of 5 plus 1, right? So we got rid of the 5 that came out, and we have 1 left. But that still leaves us work with the 243. So instead, why don't we talk about 243? We already did what 243 is. Let's go back and take a look. 243 is 243 is up here, is 3 to the 5th power. Okay, that's what 243 is, 2 to the 5th power. So it's 2 to the 5th power, 6 over 5. Okay, now we're dealing with exponents. Take a look at it. The 5 and the 5 divide out nicely. We are left with 2 to the 6. And what is, sorry, not 2, 3. I'm sorry, this was 3. 3 to the 6. I don't know what 3 to the 6 is. I know what 3 to the 4th is. I know that's 81. So 3 to the 4th, well, let's write it out so you guys can see it. 3, 4, 5, 6. So that's 9, 27, 81, right? 3 to the 4th is 81. Times 3 is 243, right? That was our 5, right? 3 to the 5th power. And multiply this by 3 again is, I don't know, 9, 2, 6, 7. Is that right? I hope it is. So 3 times 243 times 3 is 9, 2, 1, 6, 7. Yep. Okay. So the answer is 729. Would this have given us 729? It would have, if we just kept going. But you can see that by me changing it into an exponent, and then we were able to reduce those fractions, this actually was an easier way of doing it. Okay, so what else can we do with these fractional exponents? So just like before when we're multiplying powers, for example, if I say x squared times x cubed, well, how many x's do we have total? We have x to 2 plus 3, right? We add our exponents. These rules are something we talked about before. So we have x to the 5th. And if you're not sure, well, if let's say you're taking a standardized test and you forget this because you haven't done this in a while, well, give yourself this dumb example of x squared times x cubed and see what happens to these exponents. Well, don't we have a total of 5 now? So you add the exponents. If I wrote it a little differently, if I said x squared to the 3rd power, we have 1, 2, 3. So don't we have x to the 6? So we would multiply, our exponents. So if it's a power of powers, we multiply exponents. If we are multiplying powers, this is called the product of powers, we add exponents. See, the big word is add and multiply. What do we do in each situation? If I'm multiplying them, we're just having more friends to the party. That's why we're adding. But if we're exponenting them, we're adding more groups to the party. So that's why we're multiplying them. Okay, so if this is a general rule for whole numbers, does this really change for exponents? Well, if I write let's do 2 to the 1/3 times 2 to the 2/3. These aren't whole numbers. So what am I going to do? I'm going to draw like a third of a 2, and this is like a 2/3 of a 2. Oh, look. What happens to them? You know what? We follow our rules from before. And we say, you know what? If I'm multiplying exponents or powers, I then add exponents. Which this nicely becomes, oops, I shouldn't have wrote the equal sign up there. 2 to the 1/3 plus 2/3 is 3/3, which gives me a full 2 to the 1, which is just 2. Okay, what happens if I'm using, let's say 1? 1 to the, let's say 1/3 times 1 to the 1/3. What would this look like? This would look like, if I'm adding exponents, 1 to the 1/3 plus 1/3 is 1 to the 2/3. Now, let's rewrite this as a radical, just so we're kind of on the same page here. This becomes the cube root of 1 squared. Well, 1 squared is 1 and 1. The cube root of 1. Well, isn't 1 times 1 times 1 still 1? That turns out to be 1. This is a funny problem here. Let's look at this problem here. What if I wrote 12 to the 1/3 times 18 to the 1/3? Now this one follows a slightly different rule because they do not have the same bases, do they? Nor could I write 12 in a way that would match up with that 18. So I want to ask you guys to rewrite this back into the radical form. Okay, back into the radical form. And this would become the cube root of 12 times the cube root of 18. You guys are okay with that? And I wonder if you guys remember this rule. If I am multiplying radicals, we can write them over one large radical. And that's kind of what we did over here. We use our powers rule where we kind of distribute our exponent. Now take a look, don't they have the same exact exponent? This 1/3. You could rewrite this as 12 times 18 to the 1/3 power, right? If you give them little ones in the corner. And that's exactly the same thing that we're writing here. I just want to show you that we can write this in a lot of different ways. Now we can try simplifying it. This is 2 times 2 times 3. That's what 12 is. And 18 is 3 times 3 times 2, because it's 9 times 2. Now, since we're looking for sets of 3, we have 3 3s now. We have 3 2s now, and now we have 3 3s now. Hey, so if we have a pair of 3s, this is going to be just 2 times 3, which is 6. Okay. If I went ahead and wrote this in my calculator, 12 times 18, I don't know what that is. If I say 12 times 18, this is 6, 1, 2, 3, 0, 1, 8. This is 216. Is that what it is? 216. And the cube root of 216, which I don't know, but is 216 27 times 8? Because isn't 3 times 3 times 3 and 2 times 2 times 2? See, so if you tried multiplying them out, it actually becomes more work. Okay, it becomes more work. And my point is to not give you more work. Once we combine them, let's see if we can break down that 12 and 18 to find common values so we can get out of that radical as fast as we can. So if you do this way, this is more work. But instead, let's look for our numbers that we can take out, which would be faster. Okay, so let's look at this one. If I say 2 to the 3 over 4 times 8 to the 3 over 4, So can I combine these bases? There's a couple ways of doing this. We could have did what we did before. We could say, hey, this is really the fourth root of 2 times 8 to the third exponent. Sure, you could do that. That looks a little confusing. You could do that, right? We could change the 8 and to have a common base. Isn't 8 really 2 cubed to the 3 over 4? What happens to those powers? We multiply them. So we actually end up with 2 3 over 4 times 2 to the 9 over 4. This is what we converted it to. Now, what do we do when we're multiplying powers? We are adding exponents. 2 to the 3 over 4 plus 9 over 4. This nicely adds up to 2 to the 12 over 4, right? 9 plus 3. And can I simplify this last one? Would it be hard for me to simplify this last step? Well, doesn't 12 divided by 3 become pretty easy? Isn't that just 2 to the third power? Which is 8. This crazy mess, that all became 8. Oh, you could have actually changed 2 here to become 8, can't you? Because isn't 2 cubed 8? So if I wrote 2, 3 over 4, again, let's redo this problem, 8 to the 3 over 4. Isn't 2 cubed 8? So this is 8 to the 1 over 4 times 8 to the 3 over 4. Oh, let me write that a little nicer. Over 4. Now we have 8 to the 1 over 4 plus 3 over 4 is, come on. 8 to the 4 over 4. Those cancel out, and the answer is 8. Same exact answer. Well, what else could we do? If we said up here, isn't instead of multiplying this out, we could have said, well, how many 2's do we have really? We have 2 times 1, 2, 3 for 8. So we have 3 sets of that. So we actually have 2 to the 12th power. Why? Because this is 2 to the 4th, and we have 3 sets of that, so we have 12 of them. And isn't 12 divided by 4, 3? 2 cubed, which gives us back to 8. So there's a lot of different ways of getting the same answer. It depends on which way do you catch it. I can make everyone into 2's. I can make everyone into 8's. In this case, I could write it as one big radical and let them fight it out. I find the easiest for me was to change them to 2's. That was really obvious. But if you had solved that you can make them into 8, great. That was actually even less work. So just like when we're factoring, it depends on if you can catch it or not. Now, what happens if I have negative exponents? So we talked about this before. If I write x to the negative 2 power, this really means you don't belong here. You belong on the bottom of the streets. Okay? If I say x cubed times x to the negative 5, okay, this can be rewritten as x cubed over x to the 5th power, because you don't belong here. You belong on the other side of the fraction. And we can simplify the divide out to become more on the bottom. But if we use our rules like we've been doing so far, and we say, hey, you know what, x cubed times x to the negative 5, if we combine them, isn't this x to the 3 minus 5? Because I'm adding exponents, which leads us to x to the negative 2 power, which is another way of writing 1 over x squared. So you can see that all these different ways lead us to the same answer as long as we don't break any of our rules. So whatever way we feel more comfortable with, that we can remember. Now, here is a problem for us. If I say 2 to the negative 1/2 times, let's do 8 to the negative 1/2 power. So there's a couple things that we can do here. We could rewrite this by saying, hey, you know what? It's a negative, so you're really on the bottom. You're negative, so you're really on the bottom. And when you move them to the bottom or move them back to the top, the negative goes away. If we rewrite this as a 1/2 is actually a square root, and 8 is really a square root because of the 1/2 power. Hey look, I'm multiplying. This can become 1 over the square root of 8. Oh, sorry, not 8, I'm sorry, 16. 2 times 8 is 16. We know what the square root of 16 is, 1 over 4. But is there an easier way? Well, I don't want to say easier, but there is a different way. Just like what we did before, can't we make this 8 into a 2? So we have the same base. So this is 2 to the negative 1/2. And isn't 8 really 2 cubed? So I'm going to take my time writing this. So it's 2 cubed to the negative 1/2 exponent. So if you remember, I'm always writing these parentheses to remind myself that's the exponent of an exponent. So we can multiply that out to become 2 negative 1/2 times 2 to the 3 over 2 negative. We can combine that negative 1/2 and negative 3, it becomes 2 to the negative 4, right? Because we're adding exponents here. And since they're both negative, this simplifies out to become 4 divided by 2 is 2 negative. And we said negative exponents means you don't belong here. That's 1 over 2 squared, which is 1 over 4. Seems like I'm writing a lot of numbers here. But if you can practice this yourself, you'll see that, okay, I have to do this, then the next move must be this, and then the next move must be this. Seems like a lot of writing. If you want, you could have wrote this as 2 to the negative 1/2 times 8 to the negative 1/2. And since they all have the same exponent, we can write this as 2 times 8 all to the negative 1/2 exponent. 2 times 8 is 16. And 1/2 exponent is 1 over 16 square root, because 1/2 exponent is a square root, and that's 1 over 4. Oh my gosh, there's so many different ways of doing these problems. But the big deal is to remind yourself that, hey, if I'm multiplying powers, I'm adding exponents. Now this one here, 4 to the negative 4 over 5 times 8 to the negative 4 over 5. So we can write this as one big, there's a lot of different ways, but I think let's go ahead and rewrite this as a common exponent with 4 times 8. Now, if you want to go back, you can always distribute that to the exponents. 4 times 8 is 32, but instead of writing 32, I'm going to say, isn't this 2 times 2? 2 times 2 times 2? We really have 2 to the what? 2 to the 5th power, negative 4 over 5. So what is the rule that we would express here? We would do power of powers, so we're multiplying exponents. Turns out this is 4 times 5 is 20, or can't you just divide the 5s out? And we're left with 2 to the negative 4 power. This can be rewritten as 1 over 2 to the 4th, which is 2 times 2 is 4, times 2 times 2 is 4 is 16. And I feel like if you could combine them, this might be actually one of our easiest methods of solving it. This doesn't require us to change our base. This doesn't require us to write everyone as a fraction. But let's just combine it and see if we could simplify this. So that's what happens when we're multiplying. The last one today is when we're dividing. What happens when we're dividing these exponents? So if I write x squared divided by x cubed, okay, let's talk about our generic easy way, division. The rule says if we are dividing, we are actually subtracting. If they have the same base, we are subtracting, which gives us x to negative 1. And remember, you don't belong here because you're a negative exponent, you're on the bottom. To see this played out, x over x and x, you see that the x's divide out, leaving you 1x on the bottom. You have to write the 1 on top to remind yourself that this is still a fraction. So if we're dividing, we're actually subtracting our exponents. So if we write r to the 4 over 3 divided by r to the 7 over 3, how can I rewrite this as one exponent? if I am dividing, I am subtracting. So let's go and subtract those fractions. R to the 4 over 3 minus 7 over 3. Okay, 4 over 3 minus 7 over 3, they subtract out to become r to the negative 3 over 3. Hey, great, I can simplify this now. This is r to the negative 1. Negative 1 is really on the bottom. So we took something that looked really confusing with a lot of fractions, and we were able to stick to our rules. We just stick to our rules and it's simplified. Let's try another one that looks similar to this. Let's use x to the 1/3 divided by x to the 7 over 3. Because this would be terrible to do. If I try to rewrite this as a radical, right? This might confuse kids. It is not super hard, but it would just be a little more confusing. So let's first do it using our exponent ways. Since they have the same base, we can then subtract our exponents. 7 minus 1 is 6. Don't forget the negative. And we have 6 divided by 3 is 2. And we're left with 2 x's on the bottom. Now, I'm going to do this using the radical way. So if we have the same radical, remember we can write them over the same one large radical. Great. X divided by x to the 7. We can simplify x on top and 7x on the bottom. That's 1 over x to the 6. What is the cube root of 1? Cube root of 1 is, well, let me write it out for you. Cube root of 1 and the cube root of 6. That's what I'm doing in my head. Cube root of 1 is 1, and the cube root of x to the 6th power is 1, 2, 3, 4, 5, 6. I'm looking for sets of 3. We do have 2 sets. So up here is really the algebraic way, and here is more like playing with blocks, which is perfectly fine. Okay. All right, and that's it.